Hello again. So far, when we've needed to calculate a derivative, we've had to start from scratch. We've had to build a limit process and go through that entire process for each function. It turns out, though, that there are some patterns to these that we want to be aware of, and it's going to make life a lot easier for us if we know those patterns. Now, we're going to develop the patterns, and then we'll see how we can use them in a few different situations. All right, so let's start with, really the simplest of functions, the constant function. So if we let c be a constant, let's find d by dx. Let's find the derivative of the constant. All right, well, we'll start by saying, well, that's a limit. That's the limit with h going to 0. And let's treat this, the c, that's our f of x. All right, so that's the function that we're differentiating. All right, so then we'd have the limit with h approaching 0. Now, if our function is a constant, then no matter what the input is, the output is a constant, right? That's how the constant function works. So then the f of x plus h would be a constant. The f of x would be a constant, and we're dividing by h. All right, so again, let's be careful here. That first term, that's the f of x plus h. The second term is the f of x. And so then this becomes the limit with h approaching 0 of 0 over h. Now, this might look like an indeterminate form since it looks like a 0 over 0. But remember, h is not equal to 0, it's close to 0. And so if we divide 0 by a non-zero number, we get 0. And this should make sense. Remember that a constant function, if we think of the graph of a constant function, it's a horizontal line, right? So here's the graph of a constant function. This is the c value. And if we think of the derivative as representing a slope, if we have a constant function, it's a horizontal line, and the slope of any horizontal line is 0. It should seem reasonable. All right, so there's our first formula. The derivative of a constant, right, d by dx of a constant is exactly 0. Good to know. All right, what about the derivative with respect to x of x? Again, treating that as my function, then I would have the limit with h approaching 0. The f of x plus h would simply be x plus h. The f of x would simply be x over h. So then this would be the limit with h approaching 0. X minus x is 0. We have h over h. That's the limit with h approaching 0 of 1, which is 1. And again, this should be reasonable. This should make sense. If we think of the graph of the function x, the function x is the line passing through the origin with what slope? That's right, the slope is 1. The slope is 1. M equals 1 for this line. That's the graph of f of x equals x. And so again, this should be reasonable. The derivative with respect to x of x is 1. So now we've got two formulas. Let's try another one. Let's see what we've got here. What if we had x squared? All right, this is getting a little tougher. If we had x squared, then this would be the limit with h approaching 0. The f of x plus h would be x plus h squared minus the f of x would be x squared over h. So this would then be the limit with h approaching 0 of x squared plus 2xh plus h squared minus x squared over h. The x squares go to 0, right? X squared minus x squared goes to 0. We factor out the h, We remove the factor of h. Now, letting h approach 0, that second term goes to 0, and we are left with 2x. So that, again, putting that together, d by dx of x squared is 2x. Good thing to know. What about x cubed? Well, we go through the same process. Let's see, we would have limit with h approaching 0 of x plus h cubed minus x cubed over h. We expand, and let's see, expanding that cubic, expanding the binomial cubed. I've talked about this in the past. There's a pattern to this, right? That's x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed over h. Remove the common factor. Not the common factor. Remove the like terms. The x cubes go to 0, just like in the previous example, the x squares went to 0. And just like in previous exercises now, we have a common factor of h. Limit. H is approaching 0. And let's see, I'd have h by 3x squared plus 3xh plus h squared over h. It's the limit with h approaching 0 of 3x squared plus 3xh plus h squared. Now letting h approach 0, the second term and the third term go to 0, leaving us with 3x squared. So then d by dx of x cubed is 3x squared. Are we seeing a pattern? Do we see anything interesting so far? Let's go back to the previous examples. The derivative of c was 0. All right, so that's just a constant. But here I had an x to the first power. The derivative of x to the first power ended up being 1, and then there was no x. Well, remember, that's the same as writing x to the 0 power, because remember, x to the 0 is 1 as long as x is non-zero, right? Then it's an indeterminate form, but that's the same as 1x to the 0. And then we go to the examples we've seen so far. Let's look at this. The derivative of x squared ended up being 2x to the first power. And then the derivative of x cubed ended up being 3x to the second power. Any guesses? What's the derivative of x to the fourth? Well, maybe you made a guess. Let's figure it out one way or another. So let's go through the process one more time. This would be the limit with h approaching 0 of x plus h to the fourth power minus x to the fourth over h. Now x to the fourth power, that would be, x plus h to the fourth power. If we expand that, that ends up being x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth minus the x to the fourth over h. And then the same sort of process happens again. We remove the common factor of x to the fourth. We factor out the h. So we have h by 4x cubed plus 6x squared h plus 4xh squared plus h cubed over h. We remove the factor of h and let h approach 0. So this becomes the limit, h approaching 0 of 4x cubed plus 6x squared h plus 4xh squared plus h cubed. Notice that now as we let h approach 0, the second, third, and fourth terms all go to 0, and we're left with just 4x cubed. Is that what you guessed is the derivative? If so, awesome. You see the pattern. All right, so this tells us then that d by dx of x to the fourth is 4x cubed. So then you might say, well, can we go higher than that? What's d by dx of x to the fifth? Well, we're not going to go through it, but hopefully you see the pattern, and it looks like, okay, whatever was in the exponent becomes the coefficient, and then we decrease the exponent by 1. 5x to the fourth. D by dx of x to the sixth. 6x to the fifth. Seems reasonable. All right, now, so far, we've only been dealing with whole numbers. Let's look at a couple other situations. What if we wanted the derivative of 1 over x? Now remember that 1 over x, that's the same as saying that this is the derivative with respect to x of x to the negative first power. So if our power idea, if this idea we've seen so far is true, then we should be able to get that this is equal to, I'm going to put a question mark here, is this equal to negative 1 times x to the negative second? That's our question. And then remember that using algebra, I could write this instead as negative 1 over x squared. So let's sort of keep this in mind, and let's see if it's valid. All right, so then if this is our function, if 1 over x is our function, then its derivative would be the limit with h approaching 0 of 1 over x plus h minus 1 over x over h. All right, so this is a complex fraction. We've seen a technique that we can use to simplify this complex fraction. And what I can do is I can multiply both numerator and denominator by a common denominator, by the factors of the common denominator. So I'm going to multiply both numerator and denominator by x plus h by x. X plus h by x. All right, so this becomes then the limit with h approaching 0. Okay, distributing that through the first term gives me an x minus. Through the second term, the x's reduce out, leaving me 1 times x plus h. In the denominator, nothing reduces out, and I have h by x plus h by x. Simplifying in the numerator, this is the limit with h approaching 0, x minus h. The x minus x goes to 0, and I'm left with a negative h in the numerator. Hey, that's convenient because I've got a factor of h in the denominator. The factors of h reduce out. So now I have, this is the limit with h approaching 0 of negative 1 over x plus h by x. Now I can let h approach 0, and this becomes negative 1 over x plus 0, which is x, times x. It's negative 1 over x squared, which is the same as negative 1 times x to the negative second power. Our rule seems to work for this negative exponent, right? X to a negative power. Well, let's look at another example. Let's make sure it's valid for some other situations. Here I've got a square root function. And if you remember from algebra, this is the same as writing a square root function is the same as raising the x to the 1/2 power. So then, question, is this going to work out to be 1/2 times x? Now 1/2 minus 1 would be negative 1/2. And again, if we wrote this in a different form, this is the same as 1 over 2 times the square root of x. So let's put this off to the side. Let's see if I can make this work out. All right, d by dx of root x. That's the limit, h approaching 0, of the square root of x plus h minus the square root of x over h. This is an indeterminate form. I can't let h approach 0 right now because I'd give me a 0 over 0. But we've seen how to deal with situations like this. We can multiply both numerator and denominator by the conjugate of this radical expression. So square root of x plus h plus square root x over square root x plus h plus square root x. And now we go through the algebra. Limit h approaching 0. The numerator ends up being a difference of squares, right? You've got an a minus b times an a plus b. And so we would end up with root x plus h squared minus root x squared. In the denominator, I'm just going to leave that alone as h times root x plus h plus root x. This is the limit with h approaching 0. And that would give us x plus h. The square root of x plus h squared is just x plus h. Minus the square root of x squared is just x. Notice something nice happens in the numerator. X minus x is 0. And so then this is the limit with h approaching 0 of h over h times the square root of x plus h plus the square root of x. I can remove the common factor of h, leaving 1 over the square root of x plus h plus the square root of x. Now I can let h approach 0. Letting h approach 0, that's 1 over the square root of x plus the square root of x. So that's 1 over 2 times the square root of x, which is equivalent to 1/2 x to the negative 1/2. Now, we've only seen 6 examples, but it certainly seems reasonable from these 6 examples that there is a pattern forming. And let's express that pattern. And we will call this the power rule for derivatives. And we certainly have not proven this. We've only looked at a few specific cases, but we're going to accept from those cases that it's reasonable. And here's what it says. If n is a real number, then the derivative with respect to x of x to the nth power is n times x to the n minus first power. This is the power rule for derivatives. And is our first important rule to be aware of. It's critical. If you don't get this basic concept down, you're going to have issues calculating derivatives forever. Alright, so just as a quick example, if I wanted to find the derivative with respect to x of x to the negative 6th power, following this rule, right, n is negative 6, So I'd have then n. So this would then be negative 6x to the negative 6 minus 1. Now remember, you've got to be careful with arithmetic here. Negative 6 minus 1 is negative 7. So this would be negative 6x to the negative 7th, which is equivalent to negative 6 over x to the 7th power, if we wanted to write it without a negative exponent. So that's our first important rule. Now, that limits what we can do, right? We're limited to only expressions that have x to a power. So what if we had instead some function that we know is differentiable and we're multiplying it by a constant? So let's, assume that f is differentiable and c is a constant. All right, well then, if we wanted the derivative of the constant times the function, this would be the limit with h approaching 0 of c times f of x plus h minus c times f of x over h. Notice that I have a common factor of c. I can take that c outside the limit. This is then c times the limit with h approaching 0 of f of x plus h minus f of x over h. Now, if we look at this expression, the limit as h approaches 0 of f of x plus h minus f of x over h, you should recognize that as simply the derivative of the function f. So then this is equal to c times the derivative with respect to x of f of x. All right, so here we have a new formula, d by dx of c times f of x. If we want the derivative of a constant times a function, we can bring the constant outside and just calculate the derivative of the function. What if we are adding functions that are differentiable? All right, well, we're adding functions that are differentiable and we want to calculate the derivative. Okay. Limit h approaching 0. This would then be f of x plus h plus g of x plus h minus quantity f of x plus g of x. Careful with notation here. All over h. Well, I can rearrange things if I want. I can rearrange the terms. This is then the limit with h approaching 0 of f of x plus h minus f of x plus g of x plus h minus g of x over h. And I can break up the terms. Since I have a denominator of h, I can break this up as the limit with h approaching 0 of f of x plus h minus f of x over h plus g of x plus h minus g of x over h. And we know from our rules for limits that we can then take that limit and break it up term-wise. So then this becomes the limit with h approaching 0 of f of x plus h minus f of x over h plus the limit with h approaching 0 of g of x plus h minus g of x over h. And again, you should recognize these terms as simply the derivative with respect to x of f of x plus the derivative with respect to x of g of x. So, what is this telling us? If we're adding functions that are differentiable and want to calculate the derivative, we can calculate the derivatives term-wise. We don't have to think of this as one big function. We can break it up into terms. And the same thing works if instead of an addition, it were a subtraction. If this was a subtraction, we would just have a subtraction. Same, right? Works just the same. D by dx of f of x plus or minus g of x is the derivative of the f of x plus or minus the derivative of the g of x, whichever is appropriate, either the plus or the minus. All right, so now, using what we've learned so far, let's calculate the derivatives of some functions. Find the derivative of each function. All right, so here we have the function g of t is 7t to the 10th. Then the derivative of the function, all right, so then g prime of t would be 7 times the derivative with respect to t of t to the 10th. All right, so notice how I treated the 7 as a constant, and I brought it outside in a sense. Now the derivative of t to the 10th, so then this would be 7 times 10t to the 9th. Now, using a little bit of algebra, we can simplify this. The 7 times the 10 is 70. So I would write g prime of t is 70 t to the 9th power. R of p is 5 divided by p to the 8th. We don't know how to work with this function right now. All right, so what we have to do here is manipulate it. We have to turn this into a power function. So 5 divided by p to the 8th, that's the same as writing 5 times p to the negative 8th power, using what we learned in algebra. Now, the derivative, r prime of p, would be 5 times d by dp, the derivative with respect to p, of p to the negative 8th. So that would be 5 times negative 8 p to the negative 9th. Be careful there. Negative 8 subtract 1 is negative 9. Again, I can combine the 5 and the negative 8 to a single factor. So then r prime of p would be negative 40 p to the negative 9th. Now, if we wanted to write this without a negative exponent, we could write r prime of p is negative 40 times 1 over p to the 9th. And we could even go a little bit further with this. We could write this as r prime of p is negative 40 over p to the 9th. M of x is 6 times the cube root of x squared. Now we've got to be careful here. X, the power is not 2. Even though we see that x squared, it's not 2. We have to remember our rules for exponents. The cube root of x squared, that's the same as writing 6 times x to the 2/3 power. The exponent goes to the numerator, the index on the radical to the denominator of that rational exponent. All right, so then m prime of x would be 6 times d by dx of x to the 2/3. So that would be 6 times 2/3 x to the, let's see, if I have 2/3 subtract 1, 2/3 subtract 1 is -1/3. All right, and again, I can simplify these factors. 6 times 2/3 is 4. So I would maybe write that m prime of x is 4x to the -1/3 power. Now, if I wanted to write this without a negative exponent, I could write this as m prime of x is 4 over x to the 1/3 power. And if we remember what that means, as a radical, the 1/3 power is the same as the cube root. I would probably write m prime of x is 4 over the cube root of x. All right, h of x is 6x to the 5th minus 9 over x squared. Okay, so what I would do with this is I would first think of this as 6x to the 5th minus 9x to the -2nd power. That's just an algebraic step. I haven't differentiated yet. That's just algebraically manipulating, rewriting the expression. Now let's find the derivative. H prime of x. Using a combination of rules here, this would be 6 times the derivative with respect to x of x to the 5th minus 9 times the derivative with respect to x of x to the -2nd. So then this becomes 6 times 5x to the 4th minus 9 times -2x to the -3rd. And then we clean this up. 6 times 5x to the 4th, that would be 30x to the 4th, minus 9 times a negative, plus 18x to the -3rd. So I might write that. I might write 30x to the 4th minus, or plus 18x to the -3rd. Or I could write h prime of x is 30x to the 4th plus 18 over x cubed. Either of those would be acceptable. And so I hope you've seen that, maybe we could shortcut some of this a little bit. Let's look at it one more example. Suppose I gave the function that the function was 7, I think, let's use that. How about 9x to the 7th? Then the derivative, f prime of x, the shortcut is, okay, we've got the coefficient here, 9, multiply it by the exponent, 63, decrease the exponent by 1, x to the 6th. If the function, let's just call it g of x, was 12x to the -4th, then the derivative would be 12 times -4, -48, x to the -5th. All right, an application. Our function is 9 plus 8x squared plus 3x cubed minus x to the 4th. Where is the function not changing? Where is the function increasing? All right, let's think about this. Where is the function not changing? Not changing, we want the derivative to be 0. Where is the function increasing? Where is the derivative positive? That's what we need to ask ourselves. All right, so let's calculate the derivative. Let's see, the derivative, f prime of x, would be the derivative of 9. That would be 9 is a constant, so that term would go to 0. Plus, the derivative of 8x squared would be 8 times 2, 16x to the first. Plus, 3x cubed, the derivative would be 3 times 3, 9x squared. Minus, the derivative of x to the fourth would be 4x cubed. So let's clean that up. The f prime of x is negative 4x cubed plus 9x squared plus 16x. And I just wrote it in descending order because I like that better. All right, answering the first part. Where is the function not changing? Where is the derivative equal to 0? Let's solve. F prime of x is equal to 0. So that's negative 4x cubed plus 9x squared plus 16x is equal to 0. Well, I can factor out the x. I've got x by negative 4x squared plus 9x plus 16 is 0. So that tells me that x is 0. That's one place. And it also tells me that negative 4x squared plus 9x plus 16 is 0. Now this might factor, but I'm not sure. If I'm not good at factoring, quadratic formula. It's a quadratic equation, so I'll use the quadratic formula. X equals negative 9 plus or minus the square root of 81 minus 4 by negative 4 by 16 over 2 times negative 4 is negative 8. All right, let me calculate that under the radical. Let's see, what's 81 minus 4 by negative 4 by 16? That's 337. That's ugly. Okay, I'll deal with it. So that's negative 9 plus or minus the square root of 337 over negative 8. Now, if you know anything, if you remember something about how these work, if both of the signs are negative here in the quadratic formula, got that negative 9 over negative 8, we can write that instead as 9 over 8. So that's 9 plus or minus the square root of 337 over 8. And if we wanted some approximations, we could use we could find the approximations. Let me do that real quick. 9 minus the square root of 337 and divide that by 8 and the positive root. So the exact values, x would equal 0 and 9 plus or minus the square root of 337 over 8. Okay, approximately. All right, x equals 0, and x is approximately negative 1.17 and 3.42. Now, what's nice is this really, what we've done so far in part A, in this first part, really does help us in the second part. Because now I need to know, where is the function increasing? Well, we have the roots of the derivative. So now let's set up a number line. Let's see, our important numbers are at 0, at negative 1.17, and at 3.42. Those are our important values. And so now we can test into the first derivative to see if it's positive or negative in various intervals. So now let's test, how about negative 2 into the first derivative. So let's see, f prime of negative 2, and let's see, f prime of negative 2, we can just, that would be negative 2. I'm going to use the second, I'm going to use this form right here. Let me highlight what I'm using. I'm going to use this form right here. It doesn't really matter which form you use. But what I know about this is the negative 4x squared plus 9x plus 16, that's a parabola opening down. So if I just focus on this part right here, if I focus on that, that's a parabola opening down, and it has roots at negative 1.17 and 3.42. And so I know that quadratic looks roughly like this and changes from negative to positive to negative. See how that works? And so then f prime of negative 2 is going to be a negative number, right? Because x is negative, so I have a negative number. And then looking at the quadratic, negative 2 is to the left, so another negative number. That's going to be positive. I don't care what the sign is, it's positive. Now, if you don't like this, you can take the negative 2 and substitute it into the derivative. Let's see. Negative 4 times negative 2 to the third power plus 9 times negative 2 to the second power plus 16 times negative 2. Just taking the negative 2 and substituting it in to the derivative function, that gives me positive 36. It's positive. That's all I care about here. Positive. And then I do something similar. Let's test negative 1. F prime at negative 1 would be a negative number, right? Since x is itself negative. And then since negative 1 is between negative 1.17 and 3.42, that would give me a positive. Negative times a positive is negative. Similarly, if I tested, say, 1, f prime at 1 would give me a positive times a positive, which is positive. And finally, how about f prime at 5? F prime at 5 would give me a positive times a negative, which is negative. All right, where is the function increasing? It's increasing where the derivative is positive. It's increasing where the derivative is positive. So it's increasing on which intervals? Let's see. Positive, positive, this interval, this interval. So it's increasing on negative infinity to negative 1.17, roughly, and it's increasing on 0 to 3.42, approximately. All right, this video is getting a little long. Why don't we go ahead and stop here, and I'll start up another one for the rest of this topic.